Hello, everyone. This is Oluwaseun Martins, and in this second chapter of the course Mechatronic System Design 2, we are looking at signal conditioning and real-time interfacing. Now, what signal conditioning and real-time interfacing talks about is generally when you have a computer, interfacing with a real-world process while communicating data between the two of them. If you have visited probably any of these big manufacturing plants, maybe your Nestle, maybe Dangote, maybe your Lafarge, or any of these big companies, you see that you can have a control room whereby you have, an operator sit before a computer, and the person can control a belt on site, or control a bucket elevator, or control a mill, on site, and also get information from probably the load on that belt, or the uh, load within a weighing bin or something like that on that computer. So what is happening there is real-time interfacing. Or you have been to waterworks before, whereby from a console the operator can see the pressure and the volume on all the piping networks within a state just through a computer monitor, and can control a pump to start or to stop from that same computer system. That is what we refer to as real-time interfacing. So real-time interfacing in general is a term that is used to describe the aspect of connecting a computer with a real-world process and communicating data between the two. So you have uh, your monitor, your keyboard, your printer, your disk, your modem, and your CDs are familiar uh, real-time interfacing gadgets that we might be very used to. You know, a more general approach is to categorize the interfacing process into four major components, which is sensors, actuators, the computer, and the real-world process. That's just a very easy way to look at a real-time interfacing system as the sensor, actuator, the computer, and the real-world process. For instance, just a very small example, like I have explained, the real-world process might be uh, a conveyor belt. That might be the real-world process, and you have the computer. The actuator in this case is the DC motor driving the belt, and the sensor on it can be your a speed sensor on that belt, you know. But a very easy example that we can relate with is to consider the process of entering data into a computer, like you're just entering data into a computer. The you that you are entering the data, that you are viewing the output on the screen. You are the real world uh, process, and the sensor is the keyboard, you know, and it's the one that you are using to transfer information from the real world to the computer, in real time. And the monitor is the actuator in this case, transferring information from the computer back to the real world process. So this is just a very let me say, very small way to explain it so that we can understand very well. But in this chapter, we'll be looking at a broader class of reward or real-time processes, which can be human as well as machine-based. So sensors and actuators then will become components which transfers information between the electrical, computer, uh, discipline, and other disciplines, which are electrical, mechanical, fluid, thermal, or human. So that's what we're going to be looking at in this chapter. And the next subhead here is your elements of a data acquisition and control system. So your data acquisition, in some places they refer to it as DA or DQA, data acquisition system. They let your computer collect real world information through sensors. You know, your DA systems or your DQA in some textbooks allows your computer to collect real world information through sensors, maybe temperature or motion, and converts it into electrical signals that the computer can understand. So your DA systems can then display this data, process the data or save it into a file. And it can be used for monitoring process, data acquisition and control. That is your DAC. We have data acquisition. These are just systems that just acquire data. They don't do any form of control. Then we also have the data acquisition and control systems. These are systems that they do more than just acquire the data. They also can control the real world system. So these are more advanced versions that can not only collect data but also send signal back to the real world process through actuators, either motors or speakers. Like I explained, the operator sits in front of the computer, can tell the pump to start or to stop. So in that case, the operator can communicate with the real world process from his own computer. So in that case, you would have a DAC, not just a DA or a DQA, that just acquire information from the real world system. In this case, you can also communicate with the real world system. So your DAC is a system that's more advanced to your DA or your DQA that allows you to not only collect information or data from your real world processes, but also send them signal, through actuators to make adjustments on their operations. Now, that makes control and automation to be possible in these large manufacturing industries. So, for example, using a compressor highlights the difference of a DA and a DAC system. So the DA just displays sensor readings. What your DA does, data acquisition, just collect data from the real world system, just tell you what the pressure, the temperature is, maybe the weight is, and things like that. While your DAC would also adjust the speed of your plant. In this case, maybe a compressor, maybe a DC motor, maybe a conveyor belt, maybe a bucket elevator, can adjust the speed automatically using an actuator. So that's the difference between your DA and your DAC, which I've also explained earlier. And the trend is to use personal computer with a DAQ hardware. So your personal computer must have a DAQ hardware. It must have a data acquisition, hardware. That's a DAQ hardware for various applications, with the hardware connecting to the computer through ports or slots, and some computers also use wireless connectivity to run their DAQs. So you have a DA system, you have a DAC, but your DAQs are your personal computer hardwares, so that's where the difference is. So your PC-based DAQ systems, they depend on each of the following elements: the computer itself, the transducer and the sensors, the signal conditioning, the DAQ hardware, the screw terminal panel, the general purpose input / output card, that's your GPIO, and the software that is on that very personal computer. So this figure 2.11 here shows the typical PC DAQ system. You have your personal computer. It has the softwares for your DAQ. Then your data acquisition and analysis hardware, which is your DAQ here. And you have here your signal conditioning and transducer, which is, connected to the plant. So this is the arrangement of your typical PC-based DAQ system. So the overview of your input/output process will be discussed here. So the subtopic here explains how data gets transferred between a computer and a data acquisition device. So how does data get transferred between your computer and your DAQ device? So the speed of this transfer depends on three things. The speed of the transfer of data between your computer and a real-world process through your DAQ devices. The speed of that transfer of data depends on three things. Number one is the computer itself, the DAQ device also, and the way they are connected. That is the bus architecture. So the speed of data transfer between your computer and your DAQ to control or to communicate with a real-world process depends on the computer itself, depends on the DAQ device, and also the way they are connected. That is your bus architecture. And there are four main methods for transferring data, in this process. We have the direct memory access, we have the interrupted request, and also we have the programmed I/O, and also we have memory mapping type. For your direct memory access, that's your DMA. So your DMA is the fastest method where data gets moved directly between your DAQ device and the computer's memory without involving the main processor. So for your DMA, which is your direct memory access, which is the fastest method of transfer of data between your computer and your DAQs, your DAQ device, the data gets moved directly between the DAQ device and the computer memory without involving the main processor. But for interrupted request, that's your IRQ method of data transfer. In this method, your DAQ interrupts your processor to ask for permission to transfer data. So the speed at which your processor would respond, it will now determine the speed at which the data will be transferred. So the speed now depends on how quickly the processor can respond to this interruption. Unlike your direct memory access, the main processor is not even involved. The data is just transmitted directly between your computer memory and your DAQ device. But for your IRQ, which is your interrupted request, in this method, your DAQ will send an interrupt request to your processor to ask for permission to transfer data. So how quickly your processor can respond to that request will determine how fast the data will be transferred. Then we also have the programmed input/output. So in this case, it's very slow compared to the other two that we have mentioned. Why? Because the processor itself would read the data directly from the DAQ device, one piece at a time. Is the processor now that will read the data one piece at a time from your DAQ devices, and this is a very slow method. Then also we have the memory mapping. Memory mapping here, this method allows the program to directly access the DAQ memory, avoiding some software overheads, but potentially requiring special permission. In this case, the memory mapping case, the system now would have the opportunity to access the DAQ device memory, but with some level of permission to do that. That is the memory mapping method. So finally, the speed of your transfer, depends on the kind of hard drive, and the space available, So in general, the overall communication speed is directly proportional to three things: the clock frequency of the processor chip, the bit length of your bus, maybe 8 bit, 16, 32, 64, and on like that. Then also the bit length of the processor, either 16, 32, 64, and on it goes. So the higher the capacity of this specific specification of your system, the faster the speed of communication would be with your DAQ. So figure 2.12 here shows the components of your DAC system and interconnections for a system with 4 sensors and 2 actuators. Here you have the real world process here. You have your actuator here, you have your sensors here, 4 sensors and 2 actuators here. So your actuators are connected, 2 wire lines actuators, they are connected to the screw terminals of your boards, while also your 2 wires of your sensors are also connected. Then you have this connection to your CPU. You have your monitor, you have your keyboard, and this is your I/O card to which your DAC is connected. So your general purpose I/O card, your GPIOs, to set up a system for controlling external devices, with your computer for mechatronics projects. If you want to use your computer to control an external device in your mechatronics project, then you need these key components. Number one is a PC with an operating system. You can't have a PC without an operating system. It can't even work. Then also you need a general purpose GPIO card on that very system. Then you need a software driver for that GPIO card that you are using. Then you also need a termination panel and cables to connect the card to the external devices as well. So your GPIO card installs on your computer and communicates with the software through the software driver on your computer system. Then you need what we call the application software to control the devices connected to your GPIO cards. And there are 2 main options for application softwares. We have the manufacturer specific software and we have the general purpose software. For instance, if you have worked with PLCs before, you will notice that every PLC manufacturer has their own softwares that you can use to communicate between your computer and that PLC. So for instance, if you are using a Mitsubishi PLC, you need to have your Mitsubishi PLC software on your computer so that you can communicate with that PLC. Or you are using Siemens, or you are using any other type of PLCs. So for the manufacturer specific kind of software application, these software are typically limited to controlling cards from the same manufacturers, making it difficult to use multiple cards or brands together. For instance, you can't use the application software of your Mitsubishi PLC to control a Siemens PLC. It's not going to work. Then we have also the general purpose software, whereby these application software packages can work with various GPIO cards from different manufacturers, and some are better suited for data acquisition, collecting data from sensors, while others are designed for control systems, sending signals to actuators. Now, popular of such general purpose softwares are your LabVIEW, your Matrix, your Simulink, your vSIMs, which are shown in your table 2.1, which are showing some of the popular graphical application softwares that you can have. And here we have the LabTech notebook, general purpose DAC with analysis, your Lab Windows, general purpose DAC with analysis, your Workbench PC, general purpose DAC, your SnapMaster, general purpose DAC with analysis and display, your EasySet, general purpose DAC with analysis, your Onkillscope, high-speed DA, Snapshot, high-speed DA. You have Acquire, general purpose DAC. You have the LabVIEW, general purpose DAC with analysis. hyperconception, and on, Simulink, high-speed DAC with analysis and display, and on it goes. So that these are just the common graphical application softwares, that you can have on your system. Then the installation of your I/O cards and softwares. Now, before you finalize the data acquisition cards that you want to install on your system, some thought should be given to how frequently the I/O must be sampled. Number one is your sampling rate, your software impact, then your slot and I/O type, and the analog I/O. So let's just explain this briefly. Your sample rate, you need to consider how often you need to collect data, from that external or real-world process. So most GPIO cards handles 1,000 to 3,000 sample per second. So you need to consider, what is my sampling rate? How often do I want to read from this external or real-world process? That's your sampling rate. Then we have the software impact. Windows softwares might slightly slow down your sampling rate. So in this case, if you want to be using these GPIOs, you might be looking at using a Mac system or a Linux systems, because mostly Windows software would, in most cases, slow down your PC operations. So, but adjustments with the program or a stronger processor can usually compensate for this. In another case, you might just want to compensate by increasing your system capacity. Then you have the slots and I/O types. Each card takes up one slot in your computer. That's your GPIO card. So most cards often offers your digital I/O input and output and can be configured, to your needs. Then we have the analog I/Os. Analog I/Os are less common, but some cards are analog I/Os which require additional converter. For analog cards, then you have to have an analog to digital converter before your system can relate with it. So that's much that we'll be discussing in this video. In the next videos, you would have discussions on your Simulink systems. Thank you very much.